Having found the derivative of the inverse tangent or arctangent of x, let's follow a similar line of reasoning to determine an expression for the derivative of the arccosine of x. But before we go on, I want to remind you of the graphs of the graphs of the principal arccosine function and its inverse, the domain-restricted cosine function. So the domain-restricted cosine function looks just like the cosine function, the only difference being it only has function values for x values between 0 and pi inclusive. And the reason the domain is restricted is so that its inverse, the arccosine function, can actually be a function. So if we were to extend this function out like so further out, then it would fail the horizontal line test, which would mean that its inverse would fail the vertical line test and thus fail to be a function. And here we have the inverse of the domain restricted cosine function, the principal arccosine function. And here we notice the range of the arccosine function corresponds to the domain of the domain restricted cosine function. So this is pi over 2, and this is pi, and here this is pi over 2, and this is pi. And the domain of the principal arccosine corresponds to the range of the cosine. So range of the cosine is between 1 and -1, or -1 and 1, and the same is the case for the domain of the arccosine. Another way of thinking of this is that for every point x, y on the function f of x equals cosine of x, or the domain restricted cosine of x, there's a point y x on the function g of x equals the principal arccosine of x. I've put an arrow to one such example point. Here we have the point pi over 2, 0 on f of x, and that corresponds to the point 0, pi over 2 on g of x. So we know that g prime of x is 1 over f prime evaluated at g of x. In this case, that would be the derivative of the arccosine of x is 1 over the derivative of cosine, but instead of being evaluated at x, it's evaluated at the arccosine. So the derivative of sine of x, or of cosine of x, is negative sine of x, but instead of evaluating it at x, we'll evaluate it at arccosine of x. So we have 1 over minus sine of arccosine of x. We'd like to convert this sine function into an expression involving cosine. And the reason for that is if we have a cosine of an arccosine, then we'll hopefully those two operations will cancel one another out, and we can get just an expression in terms of x here. So perhaps your recollection of trig identities reminds you that sine squared of x is 1 minus cosine squared of x. If we take the square root of both sides, the left side will become the absolute value of sine of x, while the right side will become the positive square root of 1 minus cosine squared of x. And this is because square roots by definition are positive. We have the absolute value around sine of x because the sine function can either be negative or positive depending upon the value of x. So taking that into account and solving for sine of x, we get sine of x is plus or minus the square root of 1 minus cosine squared of x. If we plug back into this expression here, this expression will become 1 over this minus, and having a plus or minus in front of it, that I guess we can write it as minus plus. Instead of, we can go ahead and write it as a minus plus here. So that minus plus over the square root of 1 minus the cosine squared. But here, instead of x, you'll have the argument will be arccosine of x. If this notation confuses you, just remember that when we're plugging back in for sine of arc cosine of x, when we negate the positive square root, it becomes a negative square root. We negate the negative square root, it becomes a positive square root. When we look at cosine squared of arc cosine of x, this is asking us the question of what's the angle whose arc cosine is x, and then we take the arc cosine of that angle, so we'd expect to get x, and then we squared it. So that this just becomes 1 over minus plus the square root of 1 minus x squared. But if you look in a calculus textbook for the derivative of the arc cosine of x, you'll get minus 1 over the square root of 1 minus x squared. So what are we doing correctly? So let's look back at our derivation. So we noted that the derivative of the arc cosine function is 1 over the derivative of cosine of x, but instead of evaluating that derivative at x, we'll be evaluating it at arc cosine of x. The derivative of cosine of x is negative sine of x, but again, the sine of x will be evaluated at arc cosine of x, or I should say minus the sine of x will be evaluated at the arc cosine of x. We then went on and tried to use this trig identity to express this sine in terms of a cosine. But in doing so, we took into account the fact that sine can be negative while square roots can only be positive. So that introduced a plus or minus here. So really the bottom line is that having made the allowance for sine of x to be negative is what introduced the plus or minus here, and ultimately the minus plus in the answer. But note in this graph, the domain restriction on cosine corresponding to the principal arc cosine function is x between 0 and pi, inclusive of both. Well, what does the sine function look like over that interval? In green, we have here sine of x over that interval, and you can see it's greater than or equal to 0 over that interval. So in the interval of consideration of our problem, we don't really have to make the allowance for sine of x being negative. So in this case, the absolute value of sine of x is just equal to sine of x itself, and we can go ahead and drop this plus or minus. If we drop the plus or minus here in this expression for sine of x and we plug our result in, we will get, in place of sine of x, we'll get the square root of 1 minus the cosine squared of x, but instead of x, we'll have arc cosine of x. But here we have minus of that, the additive opposite of that, so this will take on a minus sign in front of it. We can get rid of the minus plus here. So this minus sign will just present itself as a minus sign in our answer. And this is the formula that you will see in calculus textbooks for the derivative of the arc cosine function.